The universe is choreographed by forces no one can see. 25 hidden mechanisms control the evolution of every galaxy, from the smallest dwarf to the largest spiral. Uncovering these invisible architects will completely transform how you see the cosmos. You will learn the secret rules that dictate the birth, life, and ultimate death of galaxies. What dark influence dictates the spin of a galaxy's arms, and how a sleeping dragon at a galaxy's heart can either create or destroy? What does it truly mean that we are all made of star stuff? Galaxies are not frozen portraits in space, but great, breathing entities living on timescales almost impossible for us to comprehend. Their lives unfold over billions of years, a slow cosmic dance where change is the only constant. Think of our own Milky Way, a majestic spiral that was once a shapeless cloud of primordial gas. It did not simply appear in its current form. It was built piece by piece through processes we are only beginning to understand. This grand transformation is what we mean by galaxy evolution. It is the entire life story of a galaxy, from its chaotic birth to its mature structure and eventual distant fate. To grasp the hidden forces directing this epic, we must first appreciate the players on this cosmic stage. We see a stunning variety of galaxies, from the elegant spirals with their sweeping arms to the smooth, featureless ellipticals and the irregular fragments that look like cosmic splatters. Each type represents a different chapter, a different outcome in the evolutionary storybook. Why does this matter to us right here on our tiny world? Because, as the astrophysicist Neil deGrasse Tyson so eloquently put it, we are made of star stuff. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the heart of a long-dead star. The evolution of galaxies is the story of how those raw materials were created and distributed across the universe. It is the story of our own cosmic ancestry. Understanding these vast processes is how we answer the most profound questions about where we came from and how this magnificent universe operates. With this stage now set, the real mystery begins. What are the invisible hands that guide this billion-year-long transformation? That star stuff, the very material of our being, could never have come together without an unseen framework. Think of the cosmos as a grand cathedral under construction. You see the beautiful stained glass and the ornate stonework, the visible matter of stars and gas. But holding it all up, hidden within the walls, is a massive, intricate skeleton. This is the role of dark matter, the universe's gravitational scaffolding. It is the primary hidden force, the unseen architect that dictates the very shape and stability of every galaxy. Though it makes up an astounding 85% of all matter in the cosmos, it is utterly invisible. It does not emit, reflect, or absorb light. We cannot see it with any telescope, no matter how powerful. So how do we know it is even there? The evidence comes from watching how galaxies move. In the 1970s, astronomer Vera Rubin made a startling discovery. She was measuring the rotation speeds of stars and gas within spiral galaxies. According to the laws of gravity and the amount of visible mass we can see, stars on the outer edges of a galaxy should be moving much more slowly, like planets farther out in our solar system. But her observations revealed something baffling. Those outer stars were whipping around just as fast as the inner ones. The only plausible explanation was that a huge amount of invisible matter was there, its gravity holding the entire galaxy together, preventing it from flying apart. This unseen mass, this dark matter, forms vast halos around galaxies. It acts as a cosmic glue, gathering the primordial hydrogen gas that eventually collapses to form the first stars. It dictates how galaxies cluster into immense filaments and walls, creating the large-scale structure of the universe. Without this invisible skeleton, galaxies as we know them simply would not exist. The beautiful spirals and stately ellipticals would never have taken shape, and the raw materials for planets and life would have remained scattered across a dark and empty void. This silent, unseen force is the first and most fundamental rule of cosmic construction, a ghostly presence whose gravity writes the destiny of everything we can see. But that cosmic scaffolding of dark matter is not the only silent architect at work. Deep within the heart of nearly every galaxy, including our own Milky Way, lies a sleeping dragon. This is the second hidden force, a supermassive black hole. These are not the vacuum cleaners of popular myth, but dynamic engines whose occasional roars can either nurture or devastate an entire galaxy. Their power comes from a process called feedback, and it is one of the most critical yet invisible regulators of galactic evolution. When a supermassive black hole actively feeds, pulling in vast amounts of gas and dust, it does not consume everything quietly. The material spiraling in, called an accretion disk, becomes intensely heated and can unleash a firestorm of energy. This energy erupts as intense radiation, and in some cases, colossal jets of particles that blast out across space at nearly the speed of light. This is the dragon's roar, and this outburst has a profound effect. All that energy heats the massive clouds of cold gas scattered throughout the galaxy, the very raw material needed to form new stars. Think of it like a cosmic thermostat. If the gas gets too hot, it cannot collapse under its own gravity. The feedback from the black hole effectively prevents the gas from cooling and condensing into new suns. It puts a ceiling on the galaxy's growth. This creates a fascinating self-regulating loop. As a galaxy grows and gathers more gas, some of that fuel inevitably falls toward the central black hole, feeding the dragon and making it more active. The more active the black hole becomes, the more energy it releases, which then heats the galactic gas reservoir and shuts down further star formation. It is a delicate cosmic balancing act. Without this hidden feedback mechanism, some galaxies might burn through their fuel too quickly, forming stars in a violent, unsustainable burst. Others might become far too massive. The dragon's roar, terrifying as it may seem, is essential for maintaining order. It is a hidden force that governs not through brute force, but through a subtle, energetic conversation between a galaxy and the beast at its very heart. Yet this delicate balance between dark matter and black hole feedback plays out against an even grander backdrop, a cosmic stage that is itself stretching and evolving. Think of the universe as a vast, rising loaf of raisin bread. The dough is space itself, and the raisins are the galaxies. As the loaf bakes and expands, every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough itself is stretching. This is the reality of our expanding cosmos, and it is driven by the third hidden force, dark energy. Dark energy is a mysterious, repulsive force that permeates the very fabric of space. It acts as a counterweight to gravity's relentless pull. While gravity works to bring matter together, dark energy works to push space itself apart. Its existence was first inferred in the late 1990s when astronomers observed incredibly distant stellar explosions, known as supernova. They expected to find the expansion of the universe was slowing down due to gravity, but they found the opposite. The expansion was accelerating, as if an invisible engine was steadily pressing on the gas pedal of the cosmos. This discovery was as shocking as it was profound. So what does this mean for the life of a galaxy? dark energy does not tear individual galaxies apart. Their local gravity is far too strong for that. Its influence is far more subtle, yet utterly pervasive. By controlling the rate at which the entire universe expands, dark energy dictates the future environment for every galaxy. It determines how isolated a galaxy will ultimately become. In the early universe, when matter was denser and dark energy's influence was weaker, galaxies were closer together. They frequently interacted, collided, and merged, triggering intense bursts of star formation and reshaping each other in dramatic encounters. But as dark energy accelerates the cosmic expansion, it pushes galaxies farther and farther apart. This isolates them, starving them of the fresh gas and galactic interactions that fuel their evolution. Dark energy is the ultimate background director, setting the tempo for the cosmic dance. It ensures that the vibrant, chaotic era of galaxy building is finite, gradually giving way to a future of quiet, isolated islands in an ever-darkening sea of space. This hidden force does not act on galaxies directly, but by controlling the stage upon which they perform, it seals their ultimate fate. But these cosmic architects, dark matter, black holes, and dark energy, do not work in sterile isolation. They set the stage for a drama of epic violence and beauty, a slow-motion ballet of destruction and creation. Galactic mergers are the fourth hidden force, a process of cosmic cannibalism that can completely rewrite a galaxy's destiny. This is not a fast, explosive crash, but a gravitational embrace lasting hundreds of millions of years. Two galaxies, drawn together by their mutual dark matter halos, begin a long, spiraling dance. As they draw nearer, their immense gravity starts to pull them apart. They do not simply bump into each other, they pass through one another, their structures warped and shredded in the process. You can see the ghostly evidence of these encounters in the long, streaming arcs of stars flung into intergalactic space, known as tidal tails. These are the fingerprints of a gravitational crime scene, a sign that a galaxy is being torn asunder. Yet within this chaos lies the seed of new life. When the vast clouds of gas and dust within the two galaxies collide, they do not cancel each other out. Instead, they compress. This sudden, violent pressure is like stoking a furnace, triggering a ferocious burst of star formation. Astronomers call this a starburst, a period where a galaxy can give birth to millions of new stars in a relatively short cosmic time. This is how mergers build, but they also transform. Consider the elegant spiral galaxy with its delicate arms and rotating disk. When it merges with another spiral of similar size, the orderly rotation is violently disrupted. The gravitational turmoil randomizes the orbits of billions of stars, wiping away the spiral structure and leaving behind a smooth, rounded, and featureless elliptical galaxy. This is a fundamental metamorphosis, a change in the very soul of the galaxy. Even our own Milky Way is not a peaceful island. It is a cosmic predator, currently in the process of digesting smaller satellite galaxies. And in billions of years, it is destined for its own colossal merger with the great Andromeda Galaxy, an event that will likely erase the spiral patterns we see today and forge a new, giant elliptical galaxy in their place. This process of galactic cannibalism is a relentless, hidden force that recycles the old to build the new, proving that even in the vastness of space, no galaxy is an island forever. That same gas, violently churned by galactic mergers, settles into a galaxy's circulatory system, an ocean of matter flowing between the stars. This is the interstellar medium, the fifth hidden force, and it is nothing like empty space. Picture a vast, dynamic sea, one so diffuse that in some regions a volume the size of a cathedral would contain only a few atoms of gas. Yet, this tenuous ocean is the ultimate lifeblood of a galaxy. the raw fuel from which every star is born and into which every star will eventually return. It exists in a constant state of change, a churning mix of hot, warm, and cold gas, each phase playing a critical role in the galactic life cycle. The coldest, densest parts of this medium are known as molecular clouds. These are the deep, dark nebulae, cosmic wombs where temperatures plummet and gravity takes hold. Within these frigid, dusty clouds, pockets of gas collapse under their own weight, growing hotter and denser until nuclear fusion ignites in their cores, giving birth to new stars. But for every force of creation, there is a force of regulation. When the most massive of these new stars die, they do not go quietly. They explode as supernova, unleashing unimaginable energy that tears through the surrounding interstellar medium. These titanic blasts heat vast regions of gas to millions of degrees, making it too energetic to collapse and form new stars. They also seed the galactic ocean with heavy elements forged in the stellar inferno, enriching the next generation of stars and planets. This creates a continuous, self-regulating loop, a galactic metabolism. Gas cools and condenses to form stars. Those stars live out their lives, and through winds and final, violent explosions, they recycle enriched material back into the interstellar medium. The balance between these processes, the rate of cooling versus the intensity of heating, dictates everything. It controls how brightly a galaxy shines, how quickly it forms new stars, and ultimately, how it evolves over billions of years. This invisible, churning ocean is the engine room of the galaxy, and its subtle currents write the fate of every sun that lights the cosmic dark. This galactic ocean, the interstellar medium, is threaded by a force far more subtle than gravity. Woven through the spaces between the stars is an immense, invisible spiderweb of magnetic field lines. This is the sixth hidden force, the galactic magnetic field. Though its pull is incredibly weak, trillions of times weaker than Earth's own magnetic field, its influence is pervasive and profound. These lines of force act like cosmic guide wires for charged particles, shaping the very architecture of the galaxy's gas clouds. They provide a subtle pressure that helps support vast clouds against their own weight, resisting the relentless pull of gravity that seeks to collapse them into new stars. They are the highways and the barriers for cosmic rays, those high-energy particles racing across the galaxy, steering them along invisible paths. And when new stars are born, their powerful winds and radiation can push material away. But it is often the magnetic fields that channel these outflows, sculpting them into vast, collimated jets that can stretch for thousands of light years. So where does this invisible web come from? It is not a static fossil from the early universe. Instead, it is continuously generated and amplified by a natural engine known as a dynamo. This process works within the turbulent, churning gas of the interstellar medium. As ionized gas moves, its motions, stirred by supernova explosions and stellar winds, can stretch and twist weak magnetic fields, amplifying them much like a simple hand crank can power a dynamo flashlight. Over millions of years, this turbulent motion can create an ordered magnetic structure that spans the entire galactic disk, a coherent pattern emerging from the chaos. This magnetic tapestry, though unseen, is a fundamental part of the galaxy's machinery. It does not command with the brute force of gravity, but instead guides with a gentle, persistent hand, directing the flow of material and energy in ways that quietly shape the galaxy's evolution from within. Threading through that invisible magnetic web is a constant high-energy rain. This is the seventh hidden force, a relentless bombardment of cosmic rays. These are not rays of light, but atomic nuclei, the cores of atoms, stripped of their electrons and accelerated to almost the speed of light. They are the galaxy's unseen radiation, pouring through the spaces between stars and planets, an invisible drizzle that never ceases. Though each individual particle is minuscule, their collective influence is immense, subtly cooking the interstellar medium and changing the very chemistry of star-forming clouds. When these high-energy particles slam into the cold, dense gas of a molecular cloud, they do not just pass through, they deposit a tiny amount of energy, heating the gas ever so slightly. It is a minuscule effect for a single collision, but across the vast expanse of a galaxy, this constant drizzle adds up. It acts as a gentle but persistent heating source, helping to keep the galactic gas warm and resisting gravity's attempt to cool it and collapse it into new stars. This is one way cosmic rays put a gentle brake on star formation, but they are also creators. Their immense energy can knock electrons loose from atoms, a process called ionization. Within the dark, cold molecular clouds, this ionization drives a rich and complex chemistry. It triggers reactions that form molecules, including the very building blocks of life, like water and complex organic compounds. Without this invisible particle rain, the cosmic chemistry labs inside these clouds would be far less productive. So where does this incredible rain originate? Primary particle accelerators are the shock waves from supernova explosions. These expanding shells of debris act like cosmic versions of the Large Hadron Collider, hurling particles to fantastic speeds. Another major source is the environment around active supermassive black holes, where their powerful jets can inject tremendous amounts of high-energy particles into intergalactic space. These cosmic rays carry the signature of the galaxy's most violent events, and as they travel, they become a hidden regulatory force. They contribute to the overall pressure that supports the galactic disk against gravity's pull, and they help maintain a dynamic balance within the interstellar ocean. This invisible rain, born from stellar death and black hole fury, is a quiet but essential player in the grand choreography of galactic life. Even as cosmic rays rain down, another force is at work, a silent gravitational conversation between galactic neighbors. This is the eighth hidden force, the subtle yet persistent pull of gravitational interactions and tidal forces. Galaxies are not solitary islands, they exist within a cosmic community, and their gravitational fields are in constant, invisible dialogue. Even when two galaxies never collide, their mere proximity can bend and warp one another over vast distances. The primary agent of this change is the tidal force, a differential pull that stretches an object. Think of the moon's gravity gently tugging on our oceans, creating the daily rise and fall of the tides. A passing galaxy exerts a similar pull, but on a truly colossal scale. Its gravity does not pull evenly on a neighboring galaxy. It tugs more strongly on the side that is closer. This stretches the entire galactic structure, pulling stars and gas out of their orderly orbits. The most dramatic evidence of this is the creation of immense, graceful streams of stars, known as tidal tails, which can arc hundreds of thousands of light years into intergalactic space. These are not the result of a violent collision, but of a slow, gravitational embrace. But these interactions do more than just create beautiful streamers. They can fundamentally reshape a galaxy's core. The gravitational disturbance can funnel vast reservoirs of cold gas from the outer disk down toward the galactic center. This sudden influx of fuel can do two things. It can trigger a burst of new star formation, lighting up the central regions, and it can also provide a feast for the supermassive black hole lurking there, potentially awakening it from its slumber. Furthermore, these tidal forces can trigger the formation of a galactic bar, a straight structure of stars and gas that cuts through the galaxy's center. This bar acts like a cosmic mixer, efficiently channeling material inward and further influencing the galaxy's evolution. A single, distant passage can precondition a galaxy for its entire future, setting the stage for central starbursts or black hole activity millions of years later. It is a reminder that in the cosmos, no galaxy evolves in a perfect vacuum. Its shape and its fate are continually being written by the gentle, inexorable tides from its silent partners in the dark. That gentle drizzle of cosmic rays is joined by a far more violent storm, a hurricane of energy born from the galaxy's youngest and most massive stars. This stellar feedback is the ninth hidden force, a self-regulating mechanism that acts as a galactic-scale pressure washer. Within the dark, cold nurseries of molecular clouds, the first stars to ignite are often the most colossal. These titans burn hot and fast, living lives of furious intensity that last only a few million years. But even in their brief existence, they are not quiet neighbors. They flood their surroundings with a torrent of ultraviolet radiation, and they unleash powerful, supersonic winds of charged particles that stream from their surfaces. Think of a newborn star cluster not as a peaceful gathering of lights, but as a colossal engine, and these stellar winds are its exhaust, blasting outward at millions of miles per hour. This relentless output carves vast cavities and bubbles within the surrounding gas cloud, sweeping up material and preventing nearby regions from collapsing to form new stars. It is a form of stellar birth control where the firstborn stars clear out their own nursery. Then comes the final, cataclysmic act. When one of these massive stars exhausts its nuclear fuel, its core collapses in a fraction of a second, resulting in a supernova explosion. The energy released in this single event can outshine an entire galaxy. The blast wave from the explosion slams into the remaining gas cloud with unimaginable force, shock heating it to temperatures of millions of degrees and violently dispersing it across thousands of light years. This does more than just shut down star formation locally. It seeds the wider interstellar medium with the heavy elements forged in the star's core and during the explosion itself. This creates a powerful feedback loop. Star formation creates massive stars. Those massive stars, through their winds and deaths, then disrupt and disperse the very gas clouds that would form the next generation. This ensures that star formation is a remarkably inefficient process. A typical galaxy converts only a small percentage of its available gas into stars over billions of years. Without this self-regulating force, a galaxy might burn through all its fuel in a single, brilliant, and short-lived burst. There would be no long-term evolution, no steady pacing, and likely no stable planetary systems like our own. The furious lives and dramatic deaths of the largest stars are a hidden force of creative destruction, a necessary violence that maintains the galaxy's long-term health and balance. That cosmic hurricane from a newborn star cluster is dwarfed by a far more powerful storm, one that originates from the very center of the galaxy itself. We have already met the sleeping dragon of the supermassive black hole, but when it feasts, its roar is not just a warning, it is a galaxy-altering gale. This is the 10th hidden force, the immense outflows from active galactic nuclei. Picture the central engine of a galaxy in its most violent state, a whirlpool of superheated gas spiraling into the black hole. As this material churns, it does not all fall in. Friction and magnetic fields can redirect a portion of it, launching colossal winds that blast outward in all directions. These are not gentle breezes, they are hurricanes of matter traveling at a significant fraction of the speed of light, carrying enough energy to reshape the entire galactic landscape. These AGN-driven outflows act like a cosmic pressure washer on an unimaginable scale. They plow through the galaxy's reservoirs of cold gas, the very raw material for new stars. The force is so immense that it can sweep this gas clean out of the galaxy, ejecting it into the vast, empty intergalactic medium. This process has a profound and final consequence, a state astronomers call quenching. It is the ultimate shutdown of a galaxy's star-forming engine. A galaxy that was once vibrant and blue, filled with the light of young, hot stars, is suddenly starved. Deprived of its fuel, it can no longer create new suns. Over time, the existing blue stars burn out, leaving behind the longer-lived, cooler red stars. The galaxy's color literally shifts from blue to red, and it transitions into a quiet, quiescent old age. This is the dragon's ultimate power, a direct and decisive vote on the galaxy's future. It demonstrates that the black hole is not just a passive occupant at the center, but a regulatory force capable of terminating the very cycle of stellar birth. Through these incredible outflows, a single, invisible engine can dictate the life cycle of an entire galaxy, forcing it into an early retirement across billions of years. Beyond the brilliant disk of a galaxy lies its ghostly halo, a vast and diffuse sphere that stretches for hundreds of thousands of light years. This immense structure is the 11th hidden force, an unseen reservoir that holds the keys to a galaxy's future growth. While the galactic disk is where the action happens, where stars are born and spiral arms shine, the halo is the quiet storage facility, the long-term fuel tank that dictates the pace of evolution. It is composed of an ancient population of stars, the dark matter that anchors everything, and most critically, a tenuous but immensely hot gas. This gaseous component is the halo's secret power. Over cosmic time, this hot gas can slowly cool, condensing into clouds that then rain down onto the galactic disk below. Astronomers have observed these celestial rain showers directly, spotting what they call high-velocity clouds of hydrogen gas plummeting toward the disk of our own Milky Way. This steady drizzle of fresh, pristine gas is a primary source of new fuel, replenishing the galaxy's star-forming reserves and allowing it to continue building new suns across billions of years. Without this constant, gentle inflow from the halo, a galaxy would eventually consume all the gas in its disk and starve, its star formation flickering out. But the halo's role is not just as a passive reservoir, it is also the primary gravitational anchor. The combined mass of the halo's dark matter and hot gas creates a deep gravitational well, a potential that governs the motion of everything within the galaxy. It is this halo that dictates the galaxy's rotation curve, explaining why stars on the outer edges orbit at unexpectedly high speeds. It also provides stability to the entire structure, preventing the delicate disk from winding itself too tightly or flying apart. The halo is the silent, steadying hand and the deep well of resources, a hidden force whose quiet influence ensures a galaxy can have both a stable present and a future full of possibility. A galaxy's cosmic address matters more than you might think. While the halo provides a steady rain of fuel, the wider neighborhood can exert a far more violent influence. This is the 12th hidden force, the powerful environmental effects of galaxy clusters. Imagine a galaxy not as a solitary island, but as a ship sailing through a dense, hot fog. This fog is the intracluster medium, a superheated gas that fills the vast spaces between galaxies in a cluster, a metropolis of thousands of galaxies bound together by gravity. As a galaxy moves at incredible speeds through this thin but searing plasma, it experiences a relentless headwind, a phenomenon known as ram pressure. The effect is dramatic and unforgiving. The tenuous intracluster medium acts like a cosmic sandblaster, forcefully stripping away the galaxy's own cold, dense gas reserves. This is the raw material for new stars, the very lifeblood of galactic evolution being ripped away. You can actually see the evidence in stunning astronomical images, where long, ghostly tails of hydrogen gas stream out behind a galaxy, like leaves torn from a tree in a gale. This process, called ram pressure stripping, is one of the most efficient ways to quench a galaxy. It does not just heat the gas or shut down the process, it physically removes the fuel tank altogether, leaving the galaxy starved and unable to form new generations of stars. But that is not the only pressure in this cosmic metropolis. The sheer density of galaxies in a cluster makes close encounters and gravitational disturbances a common event. These repeated interactions can pull a galaxy apart, tidally stripping its outer stars and transforming a majestic spiral into a bland, featureless elliptical. The cluster environment acts as a galactic crucible, where only the most resilient or strategically positioned galaxies can retain their structure and star-forming potential. A galaxy's fate, its very identity as a spiral or an elliptical, is not written solely by the forces within. It is profoundly shaped by the bustling, often hostile city it calls home. This reveals a deeper truth about cosmic evolution. No galaxy is an independent entity. Its life story is a tapestry woven from both its internal dynamics and the relentless pressures of the crowded universe outside. Even without a single cosmic collision, a galaxy is never truly still. Deep within its spiral arms, a quiet, relentless machinery is at work, the 13th hidden force known as secular evolution. This is the internal clockwork of a galaxy, a slow-motion transformation driven not by external drama, but by the gravitational dance of its own stars and gas. The primary architects of this change are the galaxy's internal structures, especially the stellar bars that can form in the center of many spirals. Picture this bar not as a static structure, but as a great, rotating gravitational paddle. As it turns, it exerts a torque on the surrounding gas and stars. It does not pull them directly inward. Instead, it robs them of their orbital energy, causing them to gradually drift closer to the galactic center over millions of years. This creates a cosmic river, a flow of fresh fuel channeled directly toward the nucleus. This inward rush of gas has two profound consequences. It can trigger intense bursts of star formation in the central regions, building up the galaxy's central bulge. And it can deliver a feast of material to the supermassive black hole, potentially awakening it from its slumber and activating the powerful feedback cycles we have already explored. Alongside these bars, the spiral arms themselves are not fixed structures, but rather rotating density waves like cosmic traffic jams moving through the disk. As gas clouds enter these waves, they are compressed, sparking the birth of new stars and orchestrating the grand design of the spiral pattern. This entire process of secular evolution is a testament to a galaxy's internal vitality. It proves that these vast islands of stars possess their own slow, steady heartbeat, a rhythm of change that can reshape their very form over billions of years, entirely from the inside out. This blueprint for star formation, the initial mass function, is a cosmic rulebook that dictates the destiny of every stellar nursery. It is the 14th hidden force, a statistical law that decides how many stars of each mass will be born from a given cloud of gas. Think of a vast, collapsing nebula as a cosmic lottery. The initial mass function is the rule that sets the odds, determining how many winning tickets will be for colossal, short-lived giants and how many will be for small, stable red dwarfs that will shine for trillions of years. This distribution is not a minor detail. It is one of the primary factors that sets a galaxy's entire evolutionary path. When a cloud of gas produces a top-heavy initial mass function, it means the cosmic lottery is skewed toward the high end. It creates a disproportionate number of massive, brilliant stars. These stellar titans dominate the galaxy with their intense ultraviolet radiation and powerful stellar winds, creating a harsh, high-energy environment. They live fast and die young, exploding as supernova in just a few million years. This rapid cycle of life and death floods the interstellar medium with newly forged heavy elements at a ferocious rate, enriching the galaxy's chemical makeup in a single, explosive burst. The galaxy becomes a brilliant, blue, and turbulent place, but its era of vigorous star formation is destined to be short-lived as it burns through its fuel reserves at an unsustainable pace. In stark contrast, a bottom-heavy initial mass function produces a galaxy filled with countless small, faint, and long-lived red dwarf stars. This galaxy would be far quieter and more stable. Its energy output would be gentler, its supernova rate would be low, and its chemical enrichment would be a slow, steady process unfolding over many billions of years. For a long time, astronomers assumed this cosmic rulebook was universal, the same everywhere we looked. But what if it is not? Emerging evidence suggests that the initial conditions within a gas cloud, such as its density, temperature, and even its existing metal content, might subtly shift the odds. A cloud forming under extreme pressure, perhaps in the crowded center of a galaxy or during a violent merger, might be nudged toward a more top-heavy function, producing more massive stars. This single variation would fundamentally alter the galaxy's character, changing the color of its light, the intensity of its radiation, and the very chemistry of its future planetary systems. The initial mass function is a hidden architect working at the most fundamental level, quietly writing the rules that determine whether a galaxy will be a brilliant, short-lived firework or a dim, enduring beacon in the dark. The very chemistry of a galaxy's gas is a hidden architect of its destiny. This is the 15th force, the profound influence of metallicity and chemical enrichment. Think of stars not just as lights in the void, but as cosmic alchemists, running immense nuclear forges in their cores. Throughout their lives, they fuse simple hydrogen and helium into heavier elements like carbon, oxygen, and iron. And when the most massive stars die in supernova explosions, they do not take these creations with them. They scatter their newly forged elements far and wide, seeding the surrounding gas clouds with the building blocks of rocks, planets, and life itself. This process, repeated over billions of years, gradually increases a galaxy's metallicity, which is simply the abundance of all elements heavier than helium. This chemical fingerprint is not just a record of the past, it is an active player in the galaxy's future. Gas that is rich in these heavy elements behaves differently. It can radiate heat away much more efficiently than pristine hydrogen and helium. This efficient cooling is a critical step in star formation. It allows a dense cloud of gas to shed energy, contract more easily, and ultimately fragment into new stars and planets. A galaxy with high metallicity is essentially primed for efficient star birth. Its gas cools quickly, collapses readily, and gives rise to new stellar generations with ease. You can literally read this chemical history by studying the atmospheres of a galaxy's stars. An ancient metal-poor star tells you it was born from the pristine gas of the early universe, before many supernovae had enriched the cosmos. A younger, metal-rich star reveals it was forged from gas that had already been recycled through multiple generations of stellar lives and deaths. This creates a powerful feedback loop that directly shapes a galaxy's evolution. Intense early star formation quickly enriches the gas, which then cools more efficiently, potentially leading to even more star formation. This cycle continues until other forces, like black hole feedback, step in to regulate it. Ultimately, the rise of metallicity is what makes complex structures like our solar system possible. The iron in Earth's core, the silicon in its rocks, and the oxygen in our water were all forged in the hearts of long-dead stars. A galaxy's chemical enrichment is the silent, alchemical process that transforms a simple universe of hydrogen and helium into one capable of crafting worlds and, ultimately, life. Those primordial quantum seeds imprinted across the infant cosmos grew into the gravitational wells that first gathered matter. This journey from the microscopic to the cosmic is governed by the 16th hidden force, the intricate dance of gravitational instability. Picture those tiny density fluctuations as slight bumps in an otherwise smooth, expanding sheet. Regions with just a little more mass possessed slightly stronger gravity, acting as anchors in the stretching fabric of space. They began to pull in the surrounding dark matter and hydrogen gas, slowly growing denser and more massive over millions of years. This is the essence of gravitational instability, a process of accumulation where the rich get richer. A small overdensity attracts more matter, which increases its gravity, which in turn attracts even more matter. But this growth was not unopposed. The entire universe was still expanding, a force that worked to pull matter apart and dilute these nascent structures. For hundreds of millions of years, a cosmic tug-of-war raged between the inward pull of gravity and the outward stretch of cosmic expansion. Within the vast dark matter halos, gravity finally won key battles. The gas, primarily hydrogen, began to cool. As it lost energy, it could no longer resist the halo's gravitational pull, and it cascaded inward, collapsing into the first protogalactic clouds. This was the moment of genesis, the birth of the very first galaxies from the quantum whispers of inflation. The pattern of these initial overdensities, frozen in time on the cosmic microwave background, essentially served as the cosmic blueprint. It predetermined where the great walls and vast voids of the large-scale structure would form, orchestrating the distribution of galaxies for all time. The universe did not clump randomly. It followed a map drawn in its first fleeting instant. That persistent ultraviolet glow did more than just illuminate the cosmos. It fundamentally changed the rules of galaxy formation. This era of reionization created the 17th hidden force, a pervasive and permanent ultraviolet background that has acted as a cosmic gatekeeper ever since. After the first stars and galaxies ignited, their intense ultraviolet radiation began to flood the universe. This energetic light did not travel peacefully. It violently interacted with the primordial hydrogen gas that filled all of space. The ultraviolet photons smashed into the hydrogen atoms, stripping them of their single electrons in a process called ionization. This transformed the universe from a dense, neutral fog into the transparent, ionized cosmos we observe today. But this transparency came at a cost, establishing a new environmental pressure that would last for billions of years. This ubiquitous ultraviolet background acts like a gentle but inescapable heat source. When a small cloud of gas held within a tiny dark matter halo begins to collapse to form a new dwarf galaxy, this background radiation is always there. It bathes the gas in a constant drizzle of energy, keeping it just warm enough that it cannot efficiently cool and condense. Think of it as trying to form an ice cube in a room that is perpetually just above freezing. The water will never quite solidify. This process effectively sterilizes the smallest potential galaxies, suppressing their formation before they can even truly begin. It creates a cosmic threshold, a minimum size that a dark matter halo must reach for its gravity to be strong enough to overcome this external heating and allow its gas to collapse into stars. The consequence of this hidden force is written across the sky today. It explains why we do not see nearly as many tiny, faint dwarf galaxies as our theories of dark matter alone would predict. The ultraviolet background has acted as a universal regulator, pruning the bottom branches of the galactic family tree. It ensured that the universe would be dominated by larger, more substantial galaxies, while countless potential dwarfs were quietly snuffed out, their gas kept forever warm and diffused by the ghostly afterglow of the universe's first dawn. Every massive object moving through a galaxy is swimming against an invisible current. This is the 18th hidden force, a subtle but relentless drag known as dynamical friction. It is the cosmic equivalent of wading through water, where the water itself is made of countless stars and dark matter particles. When a globular cluster or a small satellite galaxy orbits through the diffuse halo of a larger galaxy, its immense gravity does not pass unnoticed. It tugs on the surrounding stars as it moves, pulling them slightly toward it and creating a gravitational wake, a dense trail of stars following behind it like the bow wave of a ship. Crucially, this wake does not simply vanish. Its own collective gravity reaches out and pulls back on the object that created it. This is the friction, a braking force that steadily saps the object's orbital energy. The effect is not a sudden stop, but a gradual, inevitable decay. Over hundreds of millions of years, this drag causes the object's orbit to shrink, forcing it to spiral slowly inward toward the galactic center. This process is a primary delivery mechanism for the supermassive black hole lurking at the galaxy's heart. Dynamical friction gently guides entire satellite galaxies and massive star clusters on a one-way trip to the core, where they are eventually torn apart and consumed, feeding the central dragon and potentially triggering new outbursts of activity. But its influence does not stop there. Even within the galaxy's disk, the same force acts upon immense internal structures. A large stellar bar rotating through the dense field of stars experiences this same gravitational drag. Dynamical friction causes the bar to slow down over cosmic time, transferring its energy to the surrounding stars and causing the bar itself to weaken or even dissolve. It is a universal sculptor of galactic cores, a quiet, persistent force that ensures nothing truly massive can orbit forever unchanged, continually drawing both the largest structures and the smallest satellites toward their eventual fate at the very center of the gravitational whirlpool. That ghostly ultraviolet background is not the only environmental pressure shaping the galactic population. When we peer deep into space, we are also looking back in time, and the view reveals a startling transformation. Distant galaxy clusters, observed as they were billions of years ago, are filled with a surprising number of vibrant, blue, star-forming spirals. Yet, nearby clusters in the modern universe are dominated by red, dead, and smooth elliptical galaxies. This dramatic shift is the 19th hidden force, known as the Butcher-Oemler Effect. It is a powerful testament to how a galaxy's neighborhood can rapidly and efficiently rewrite its destiny. The effect is named for the astronomers who first quantified this cosmic makeover, and it provides a direct snapshot of evolution in action. It reveals that the dense cluster environment acts as a galactic factory, systematically processing infalling spiral galaxies and transforming them into the quiescent ellipticals we see today. But how does this factory work? The process is brutal and multifaceted. As a spiral galaxy first plunges into the crowded cluster, it meets the searing hot intracluster medium. The immense ram pressure, like a cosmic headwind, violently strips away its cold, dense gas, the very fuel for new stars, starving it almost immediately. At the same time, the galaxy experiences constant gravitational harassment from near misses with other cluster members. These repeated tidal interactions pull and distort the galaxy, randomizing the orderly orbits of its stars and effectively erasing its delicate spiral structure. The galaxy is essentially sandblasted and gravitationally shaken until its star formation is quenched and its morphology is permanently altered. The Butcher-Oemler effect is not a slow, gentle decline. It is a relatively rapid quenching, a galactic assassination that can occur within a billion years of a galaxy falling into the cluster's grip. This hidden force demonstrates that a galaxy's form and future are not solely determined by its internal clock, but are often decided by the violent, transformative pressure of the city it moves into, a stark reminder of the power of place in the cosmos. Our own Milky Way galaxy sails through space with a ghostly entourage. Dozens of dwarf satellite galaxies, faint and diffuse, orbit in its vast gravitational wake. These are not merely celestial decorations, they are the 20th hidden force, silent partners that actively sculpt the giant they accompany. Their subtle, persistent gravity creates ripples throughout the galactic disk, like stones dropped into a pond of stars. These gravitational perturbations can compress gas clouds as they pass, stirring up the calm waters of the interstellar medium and triggering localized bursts of new star formation. This is not the violent starburst of a major merger, but a gentler, ongoing stimulation, a way for the large galaxy to keep forming stars without a colossal collision. But these satellites offer more than just a gravitational nudge. They are also a source of fresh material. Over billions of years, the relentless pull of the larger galaxy slowly strips these dwarfs of their stars and gas. This captured material is then accreted, adding to the mass of the galactic halo and providing new fuel for the disk itself. You can see this process happening right now in our own cosmic backyard. The Sagittarius dwarf spheroidal galaxy is currently in the act of being torn apart by the Milky Way's gravity. It has been stretched into a great river of stars that wraps around our entire galaxy, a shimmering streamer visible to our telescopes. This is not a relic of the ancient past, it is a live demonstration of galactic cannibalism on a small scale. Every star in that stream is a testament to the continuous, slow-motion assimilation that helps build a giant galaxy piece by piece. These silent, orbiting dwarfs are both architects and fuel, their gradual destruction contributing to the ongoing growth and evolution of the cosmic titan they call home. Some of the cosmic rays raining down on our galaxy carry energies of almost unimaginable magnitude. These are the ultra-high energy cosmic rays, atomic nuclei traveling with the kinetic energy of a well-thrown baseball packed into a single subatomic particle. Their existence presents a profound cosmic mystery. According to a prediction made by physicists Greisen, Zatsepin, and Kuzmin, there should be a natural ceiling, a GZK cutoff, for how much energy these particles can retain across intergalactic space. The entire universe is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. For a proton traveling near the speed of light, these microwave photons are not gentle whispers, they are a dense fog of high-energy gamma rays. When an ultra-high energy cosmic ray collides with one of these background photons, it loses a significant amount of its energy, like a ship constantly battling against a powerful headwind. Over distances of hundreds of millions of light years, this interaction should sap the energy of the most powerful particles, effectively creating a cutoff point beyond which we should detect almost nothing. Yet we have detected them. This is the mystery of the GZK cutoff, the 21st hidden force. The fact that these particles reach us at all means they cannot have traveled from the farthest reaches of the universe. They must originate from relatively nearby on the cosmic scale, within our local supercluster of galaxies. This turns them into cosmic messengers from the most violent engines in our neighborhood. The primary suspects are the active galactic nuclei we have already met, with their colossal jets powered by supermassive black holes. These jets are nature's ultimate particle accelerators, capable of hurling matter across space with forces that dwarf anything we can create on Earth. The propagation of these rays is a story written by the hidden magnetic fields of intergalactic space. As these charged particles travel, The faint, vast magnetic fields woven between galaxies gently bend their paths, steering them on winding, unpredictable routes. By studying their arrival directions and energies, we can work backwards not to find a single source, but to map the invisible magnetic topography of the cosmic voids. This helps us understand the distribution of matter and energy on the largest scales, the very environment that cradles galaxy clusters and dictates how they interact. The presence of these ultra-high energy particles is a subtle but potent environmental factor. When one of these rare, unimaginably powerful particles slams into a galaxy, its immense energy can ionize the tenuous gas in the galactic halo, potentially influencing the delicate thermal balance that governs whether gas cools and falls in to form stars. They are the ultimate probes of the universe's most extreme conditions, and their silent, relentless journey through the cosmic web quietly shapes the conditions for galactic life. That shadow on the cosmic microwave background is not an absence of light, but a story of immense energy. When the ancient light from the Big Bang, the cosmic microwave background, journeys across the universe, its path is not always clear. If it passes through a massive galaxy cluster, it encounters a seething ocean of superheated electrons within the intracluster medium. These electrons are so energetic that when a microwave photon from the background radiation collides with one, it gets a significant kick, a boost in its energy. This process, known as the Sunyaev-Zeldovich Effect, creates a unique and subtle distortion, a specific kind of shadow imprinted on the most uniform light we can observe. It is a direct signature of the incredible heat and pressure that exists within these cosmic metropolises. This hidden force is a powerful tool for cosmic cartography, allowing astronomers to find the most massive clusters in the universe, regardless of how far away they are. Because the effect depends on the sheer number of hot electrons, it directly reveals the total gas pressure inside the cluster, a measure of its raw gravitational might. But this pressure is not just a static number, it is a dynamic record of the energetic battles being waged within. What keeps this vast reservoir of gas so hot, preventing it from cooling and flooding the cluster with new stars? The answer lies in the very feedback processes we have explored. The powerful outbursts from supermassive black holes in active galactic nuclei pump tremendous energy into the intracluster medium, like a central heating system for an entire cluster. The Sunyaev-Zeldovich effect gives us a way to measure the results of this feedback. By studying these distortions, we can quantify how effectively the central black holes are regulating their environment, preventing catastrophic cooling and maintaining the delicate balance that dictates whether a galaxy within the cluster continues to form stars or is forced into a quiet retirement. It is a hidden force that allows us to see the invisible hand of black hole feedback, written in the subtle shadows on the afterglow of creation. This cosmic assembly line, where small pieces build into giant structures, is the 23rd hidden force, the hierarchical structure formation model. The universe did not build its grandest cathedrals all at once. It began with the smallest bricks laid down by gravity in the wake of the Big Bang. The first structures to condense out of the primordial soup were not majestic spirals, but tiny, dark matter halos, each no more massive than a modest star cluster. These minuscule gravitational wells were the universe's true pioneers, the seeds from which everything else would grow. They began to merge, two small halos coming together to form a larger one, which then attracted and merged with others. This process of cosmic consolidation has been running for over 13 billion years, a relentless, bottom-up construction project on the grandest possible scale. Within these growing dark matter halos, the first pockets of gas began to cool and collapse, igniting the very first stars and assembling the first, faint proto-galaxies. These building blocks were the galactic equivalents of pebbles, and through a continuous process of collisions and mergers, they steadily built up into the boulders and then the mountains of the modern cosmic landscape. Our own Milky Way is a product of this endless cycle. It was not born a giant, but grew by consuming hundreds of these smaller predecessors, a history written in the stellar streams that still wrap around it like cosmic scars. Supercomputer simulations of the universe vividly bring this process to life, showing how the faint ripples observed in the cosmic microwave background evolve, over billions of years of simulated time, into an intricate cosmic web of filaments and clusters that perfectly mirrors our own observed universe. This hierarchical model is the overarching narrative, the grand story arc that gives context to every other hidden force. Galactic mergers, black hole feedback, and stellar winds are not isolated events. They are the dramatic scenes and character conflicts within this much larger epic of assembly. It is the hidden framework that assures us the universe has a coherent history, a story of constant becoming where even the largest galaxy owes its existence to the humble aggregation of the very smallest things. These elegant correlations are not just for cataloging galaxies, they are windows into a deep, hidden order. Amidst the chaos of galactic collisions and stellar explosions, there exists a remarkable consistency, a set of cosmic rules that link what we can see to the invisible forces at work. The 24th hidden force is revealed in these empirical scaling relations, the Tully-Fisher and Faber-Jackson relations. They are the universe's own accounting system, balancing the books on galactic scales. For a spiral galaxy, the Tully-Fisher relation states a simple, profound truth. The faster a spiral galaxy rotates, the brighter it is. Its total luminosity is tightly locked to its rotational speed. You might think a galaxy could have any combination of spin and brightness, but the data reveals an incredibly precise correlation. It is as if every spiral galaxy is built to a specific blueprint where its speed dictates its light output. For elliptical galaxies which do not rotate in a clean disk, the Faber-Jackson relation provides a similar rule. It connects a galaxy's brightness to the random, disordered motions of its stars, a property known as velocity dispersion. The more furiously the stars inside an elliptical galaxy jostle about, the more luminous that galaxy will be. These are not mere curiosities, they are direct consequences of fundamental physics, specifically the virial theorem. This theorem describes the balance between kinetic energy and gravitational potential energy in a stable, bound system. In essence, the motions of the stars and gas, whether orderly rotation or chaotic jostling, are a direct measure of the total gravitational pull holding the galaxy together, which in turn is dictated by its total mass, including the immense, invisible dark matter halo. The luminosity then emerges from the number of stars that mass can form and sustain. This is why these relations are so powerful for measuring cosmic distances. By simply measuring a galaxy's rotation speed or stellar velocity dispersion, an astronomer can use these relations to determine its intrinsic brightness. Comparing this intrinsic brightness to how dim it appears from Earth instantly reveals its distance, turning entire galaxies into standard candles for mapping the vast expanses of the universe. But beyond their practical use, these scaling relations are a fundamental test for our theories of galaxy formation. Any successful model must explain why galaxies, born from such turbulent and varied histories, consistently fall onto these precise lines. They are a silent, mathematical testament to the underlying order governing the cosmic evolution of every island of stars. The grand cosmic architecture, from the faintest dwarf galaxy to the mightiest cluster, finds its ultimate origin in a realm of pure probability. This brings us to the 25th and most profound hidden force, quantum fluctuations and the seething energy of the vacuum. we must journey to the smallest conceivable scale, a trillion times smaller than an atom, to find the genesis of everything we see. Empty space is not truly empty. According to quantum mechanics, it is a vibrant, foaming sea where pairs of virtual particles and antiparticles constantly flicker into existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and vanishing. This perpetual, chaotic dance is not without consequence. The collective energy of this quantum foam, known as vacuum energy, is believed to be the very engine behind the cosmological constant, the simplest explanation for the dark energy that is accelerating the expansion of the universe. The same force that governs the largest scales of cosmology is born from the smallest, but its role is even more fundamental. Recall the inflationary epoch, that moment of hyper-expansion in the universe's first instant. During that period, the microscopic quantum fluctuations in the inflating field were not smoothed away. Instead, inflation stretched them, magnifying these tiny probabilistic ripples to cosmic proportions. These magnified ripples became the slight variations in density, the overdensities and underdensities that gravity would later seize upon. They were the primordial seeds, the cosmic blueprint for everything that followed. Every galaxy cluster, every vast filament of the cosmic web, and every solitary void can trace its lineage back to a random, infinitesimal flicker in the quantum vacuum during the universe's first fraction of a second. This is the ultimate hidden connection, the probabilistic, counterintuitive rules of the quantum world, which dictate that something can emerge from nothing, are directly responsible for the grand classical structure of the cosmos we inhabit today. The very existence of our Milky Way and every star within it was once nothing more than a statistical possibility in the seething heart of nothingness. These 25 forces are not solo performers, but a single, intricate symphony. Each one, from the quantum whisper to the galactic roar, is part of a vast, interdependent web. Think of it as a galactic ecosystem. Dark matter provides the unchanging stage and the gravitational framework. The baryonic processes of stars, gas, and magnetic fields are the actors, playing out the drama of creation and destruction. And dark energy is the conductor, setting the tempo for the entire cosmic theater by controlling the expansion of the universe itself. The true magic and the grand challenge for modern astrophysics lies in how these forces interact, balancing and competing in a dance of breathtaking complexity. Consider a single cascading sequence. A galactic merger, the violent dance of two spirals, does more than just create an elliptical galaxy. It violently funnels immense amounts of cold gas toward the center of the new galaxy. This incoming torrent of fuel has two immediate fates. It can ignite a ferocious starburst, lighting up the core, but it can also plunge directly toward the supermassive black hole. This feast awakens the sleeping dragon, triggering powerful AGN feedback. The black hole roars to life, launching jets and winds that blast back out through the galaxy. But even this outburst is not a free-for-all. The galaxy's pervasive magnetic fields, that invisible spiderweb, act to channel and shape these outflows, focusing their energy and determining exactly how they will heat the surrounding gas and quench future star formation. One event, a merger, directly influences black hole activity, which is then modulated by magnetic fields. This is just one thread in the tapestry. The initial mass function determines how many massive stars are born, which dictates the strength of stellar feedback, which then enriches the interstellar medium with metals, which in turn affects how efficiently the next generation of gas can cool and form new stars. It is an endless, self-referencing loop. Understanding this delicate interdependence is the key. Why does one galaxy blaze with youth while its neighbor slips into a quiet red retirement? The answer is not in a single force, but in the unique balance and sequence of all 25, a recipe written in the language of physics that gives each galaxy in the sky its own unique story and personality. These hidden symphonies of force would remain silent without the eyes and ears we have built to listen. Our window into this cosmic drama is a suite of technological marvels, each designed to translate a different whisper from the dark. We peer behind the curtain not with a single tool, but with an entire orchestra of observatories, both on the ground and in the pristine darkness of space. Giant telescopes like the Very Large Telescope in Chile capture the faintest visible light from galaxies billions of light years away, while space-based observatories like the Hubble and the James Webb Space Telescope see far beyond what our atmosphere allows. Each sees the universe in a different light, literally, by observing across the entire electromagnetic spectrum, from the long, slow waves of radio to the incredibly energetic spikes of gamma rays. We assemble a complete picture. Radio telescopes reveal the cold, dark hydrogen gas between the stars, the raw material of future suns. Infrared eyes, like those on the James Webb, pierce through obscuring dust to witness the birth of stars hidden within cosmic nurseries. X-ray observatories detect the searing heat of gas trapped in galaxy clusters or blazing around black holes. Every wavelength tells a different part of the story. But simply taking a picture is not enough. We must dissect the light itself to read the fine print. This is the work of the spectrograph, an instrument that acts like a cosmic prism, splitting a galaxy's light into a detailed rainbow or spectrum. Within that rainbow are dark lines like a unique barcode. The positions of these lines reveal the galaxy's chemical composition, showing us the iron, oxygen, and carbon forged in its stellar furnaces. Their subtle shifts tell us if the galaxy is spinning, moving toward us, or racing away, allowing us to measure the invisible grip of dark matter. Even the faint polarization of light, a slight alignment of its waves, can betray the presence of those vast, invisible magnetic fields threading the galactic void. These are not just tools, they are our extensions into the cosmos, our only means of transforming faint photons that have traveled for eons into a coherent narrative of the forces that have shaped our universe from its very beginning. These digital universes run on some of the most powerful supercomputers on Earth, machines that crunch numbers for months to simulate over 13 billion years of cosmic history. In these virtual labs, scientists begin with the initial conditions we observe in the cosmic microwave background, that faint afterglow of the Big Bang. They then program in every known law of physics, from the relentless pull of gravity and the complex flow of gas hydrodynamics to the subtle influences of magnetic fields and the explosive energy of supernova and black hole feedback. Pressing start is like launching a new universe, one where they can watch galaxies form, collide, and evolve in a breathtakingly accelerated timescale. The goal is not to create a perfect replica of our specific Milky Way, but to see if the same basic ingredients and rules can produce a realistic population of galaxies with the right mix of spirals, ellipticals, dwarfs, and giants. The most advanced simulations with names like Illustris TNG and Eagle have done exactly that. When you look at the galaxies that emerge from these virtual runs, they are uncannily familiar. They possess the correct sizes, shapes, and colors. They follow the Tully-Fisher and Faber-Jackson relations. Their stars have the right chemical compositions. They even display the intricate cosmic web of filaments and voids that we observe in our own universe. This remarkable agreement is a powerful vote of confidence. It tells us that our understanding of the 25 hidden forces, while incomplete, is fundamentally correct. We are missing pieces of the puzzle, certainly, but the main actors on the cosmic stage have been identified. These simulations also reveal something profound about the nature of scientific discovery. We cannot run a controlled experiment on a real galaxy, but we can run countless experiments in a virtual one. Scientists can tweak the code, turning off black hole feedback, for instance, to see what happens. In those altered universes, galaxies often become far too massive and bright, confirming that the dragon's roar is essential for regulation. This virtual experimentation allows us to witness the consequences of our theories, providing a dynamic, evolving test bed for the hidden forces that shape our reality. Even with these magnificent tools and simulations, our understanding of the cosmos remains wonderfully incomplete. The 25 hidden forces have given us a framework, a cast of characters, but the deepest mysteries about their true nature and interactions persist. We still do not know what dark matter is made of, only that its gravitational ghost holds galaxies together. We call the force behind cosmic acceleration dark energy, but its origin is a profound puzzle that challenges the very foundations of physics. And while we see the effects of black hole feedback, the precise mechanics of how energy couples to galactic gas, how the dragon's roar is translated into a galactic scale wind, remains a subject of intense and ongoing investigation. Are there even more fundamental laws of galaxy formation, principles we have not yet even conceived, waiting to be discovered? The journey is far from over. A new generation of cosmic observatories is poised to revolutionize our view. The Vera Rubin Observatory will conduct a 10-year movie of the sky, cataloging billions of galaxies and watching for subtle changes that reveal dark matter's distribution. The Square Kilometre Array, a vast radio telescope, will map the cosmic web of neutral hydrogen from the dawn of time, tracing the raw material of galaxy formation itself. The Nancy Grace Roman Space Telescope will peer into the heart of dark energy, measuring its influence across cosmic history with unprecedented precision. These instruments will not simply provide more data, they will offer entirely new dimensions of understanding, allowing us to test our theories against a census of the universe so vast it will feel like seeing the cosmos for the very first time. This is the beautiful, unending cycle of discovery. Each answered question inevitably reveals a dozen new, more profound ones, each more tantalizing than the last. The story of galaxy evolution is not a book we are finishing, but a narrative we are actively writing, an invitation to forever look deeper into the dark and wonder what hidden forces we will uncover next.